Hello everyone and welcome back to the channel. I am Raju Saran, and in this digital logic series we will learn the fundamental concepts that form the backbone of modern digital systems and computer engineering. Whether you are preparing for university examinations or strengthening your fundamentals or simply curious about how digital circuits work, this course is designed to help you understand the concepts clearly and systematically. In today's lecture, we are going to learn one of the most important topics in digital logic, that is simplification of Boolean functions. At first glance, Boolean expressions may seem like just combinations of variables and logic operators. However, in practical digital systems, simplifying these expressions can save hardware, reduce power consumption, decrease cost, improve speed, and make circuits easier to design. Let's begin with a simple question. Suppose you are traveling from Kathmandu to Pokhara. There may be several possible routes, but naturally you would prefer the route that reaches the destination with the least distance, least fuel consumption, and least time. Boolean simplification follows the same principle. Different Boolean expressions can produce exactly the same output, but some expressions require fewer logic gates and fewer connections. As engineers and IT students, we always prefer the simpler implementation. Okay, first thing first, why do we simplify Boolean functions? Imagine you have two methods to turn on a light. In first method, you pass the current through 10 different switches connected in a complicated arrangement. In second method, you pass the current through 10 switches. Sorry, in second method, you achieve the same result using only 3 switches. Now tell me, which method would you choose? Obviously the second one. Similarly, in digital electronics, fewer gates means lower hardware cost, less power consumption, reduced circuit complexity, faster operation, and higher reliability. This is why Boolean expression simplification is so important. Let's try to understand this with a real life analogy. Please don't directly write this in examination. I'm just trying to teach you with a real life analogy. This is not a real case with digital gates. Okay, imagine a college attendance rule where a student is allowed to sit in examination if he or she is final year student, which is being represented by condition A if A is true, and he or she paid fees, which can be represented by condition B. It's a normal process, right? You are allowed to sit in examination if you are a final year student, which is represented by A, and he or she had paid fees, which is represented by B. Okay, and another way to be qualified for the examination is if he or she is final year student, which is same to the previous one represented by condition A, and he or she has special permission, like sometimes you go to the principal's office and ask her to sign on a cheat, which is represented by C. In both the cases you are allowed to sit on examination, right? Either you are final year student and you have paid all the fees, or you are final year student and you have special permissions. And mathematically this can be represented by function f is equals to ab plus ac, where function f means if student is allowed to sit in examination or not. Its value can either be 1 or 0, right? And first one, first condition can be mathematically represented as either Either the student is final year student and he or she had paid all the fees. You can see in between the A and B condition there is a multiplication sign, right? Multiplication means and get, right? And another case is either he is a final year student and he or she has special permissions, and there is a and get in between these two conditions. And we also have to mention or get in between these two conditions, so it can be represented mathematically like this. Here we can see that there are three gates in total. One, here you can see and gate, this is or gate, and this is and gate. Now here is one thing to notice: the condition A, which means final year student, is repeated two times, and by utilizing Boolean laws we can rewrite the same expression as f is equals to a b plus c. Now the rule becomes easier to understand. This means a student is allowed to appear in the examination if he is a final year student and must be either have paid all the fees or obtained special permission. Okay, the gate has reduced to only two. There is only one AND gate and one OR gate. This is called simplification of Boolean expressions. The expressions simply become more efficient. This is the essence of Boolean simplification. Let's try to understand this with another example. We can take another Boolean expression f is equals to a plus ab. Here you can take a as common and we can write 1 plus b. In this example also, the number of gates is reduced from 2 to 1. But you can argue that here we can clearly see 2 gates. But you are saying the gates are reduced to 1. How is that even possible? Let's make the situation more clear, okay? In this stage, you are supposed to already know all the Boolean laws, okay? One of the Boolean laws, known as absorption law, states that in OR gate, which is represented by this symbol, if one input is any of the variables and another input is 1, then the output is always 1. This is called absorption law. So this expression can be further reduced as f is equals to a and 1, since 1 plus b is equals to always 1. This is called absorption law. Okay, so finally f is equals to a is your simplified expression. We can clearly see that the number of gates is reduced from 2 to 2 gates to 0 gates. Here we can see only one gate, but another Boolean law says that a and 1 is only a. This can be explained by making a logic gate. If the input is 0, if the value of a is 0, the AND between 0 and 1 is always 0, and if the input is 1, the AND between 1 and 1 is always 1. That means we can write, if the input is a, the output is also a, if other input of the AND gate is 1. Okay, so finally we reduce the number of gates from 2 gates to 0 gates. This is called simplification, right? Let's take another example. Exercise 2. Consider f is equals to ab plus a complement b. Pause the video for a while and try to simplify it by yourself. Notice that b is common, so you can factor the b out. But we know that a plus a complement is always 1, so you can replace f is equals to b dot 1, which is further simplified as b, since ending with 1 always result to the input. Dramatically, the entire expression just simplified to b. What initially looked like a complicated circuit actually can be implemented using a direct connection, which is b. Let me make you understand this with one practical application in engineering. Let's consider your smartphone. Every time you unlock your phone, thousands of logic operations occur inside the processor. Modern processors contain billions of transistors. Imagine if engineers never simplified Boolean expressions, the processor would require more transistors, consume more power, generate more heat, and reduce battery life. Boolean simplification directly contributes to faster processors, longer battery life, smaller chips, reduced manufacturing costs. Every smartphone, laptop, router, your smartwatch, or any other digital watch, or any other digital devices benefits from this concept. We can also take another example of traffic light. Suppose a smart traffic light system runs a green signal when when traffic density is high and emergency vehicle is detected. This is a condition for green light, okay? Or traffic light is green when traffic density is high and manual override activated, right? Generally, if the traffic density is high, the green light is off, there is red light, right? But we can write the logic. Even if the traffic density is high and emergency vehicle is detected, like in conditions like there is ambulance or fire brigade or any other emergency vehicle is detected, the light should go green, right? Similarly, if traffic density is high and manual override is activated, if there is a manual switch for green light and the traffic police tries to activate the green light manually, then also the green light should go on, right? And mathematically this can be represented as let me write the function with f is equals to, the first condition is a, and is represented by multiplication symbol, and emergency vehicle is detected, that is b, or can be represented as plus symbol, or traffic density is high and manual override is activated, that is c. This is mathematical expression or Boolean expression, and this expression can be simplified as a b plus c, and this reduces the number of gates, right? We can count the number of gates: 1, 2, 3 in first initial expression, there are three logic gates required, two AND gates and single OR gate. But in the simplified form, there is only one AND gate and one OR gate, right? Instead of checking traffic twice, like in the previous case, the controller checks traffic once, and then evaluates the second condition. This results in a more efficient digital circuit. And there are two major approaches for simplification of Boolean expressions. One is Boolean algebra, and second one is K-map, also known as Karnaugh map. Karnaugh Karnaugh map. Karnaugh map provides a graphical method that becomes especially useful when dealing with multiple variables, and it is much simpler, easier to simplify complex Boolean expressions using a Karnaugh map rather than Boolean algebra. While solving the complex Boolean expressions using the Boolean algebra, you have to by heart and learn all the Boolean laws. That is important if you want to solve using Boolean algebra. But using Karnaugh map, there are certain set of rules that you need to follow, and it is much simpler and less complicated than Boolean algebra. But in examination, you might be asked to solve the problem using the Boolean algebra or Karnaugh map. So you have to study both. Remember one thing: Boolean simplification is not about changing the logic. It is about finding the simplest possible expression that produces exactly the same output. Think of it like taking the shortest route to a destination, or using fewer words to convey the same meaning, or building a machine with fewer parts while keeping the same functionality. The result remains the same, only efficiency improves, and that comes with a whole lot of other benefits at the same time. So in today's lecture, we learned what Boolean simplification is, why simplification is important, and this can also be asked in examination in 2 marks, why the simplification is important, right? How it reduces the hardware requirements, and few real world analogies to understand this concept, practical applications in digital systems, a few examples. In next lecture, we will cover the complex questions that can be asked in examinations, and few other topics like min terms and max terms, right? And little complex questions that can be asked in the exam. That brings us to the end of today's lecture. I hope this topic is now much clearer and easier to understand. If you found this video helpful, please like the video and share it with your classmates who may benefit from it. If you have questions, feel free to leave them in the comment section, and I will do my best to address them in future lectures. If you are a student from Apex College, you can directly ask me in classroom, or either you can visit the faculty. In next video, we will discuss more about simplification and solve more practical questions related to the simplification. Thank you for watching. Bye bye.